The world you perceive right now, the screen in front of you, the weight of your body, the passage of time, presents itself as immediate and indisputable. There's no deliberation required. Objects occupy definite locations. Events follow one another in sequence. Solid things remain solid. Yet the mathematical structure physicists use to describe this same reality at its most fundamental level contains none of these features. The equations that govern atoms, light and force describe something fundamentally probabilistic, non-local, and without intrinsic definiteness until the moment of measurement. This creates a peculiar dissonance. The most successful physical theory in history produces predictions of staggering accuracy. Yet the world it describes bears almost no resemblance to the world we inhabit. This isn't a problem of insufficient data or experimental limitation. Quantum mechanics has been tested across 9 orders of magnitude in energy scales and consistently validated. The issue runs deeper. The theory works perfectly as a predictive tool while simultaneously resisting any straightforward interpretation of what it says about the nature of physical reality itself. Most working physicists simply use the formalism without dwelling on this interpretive gap. Calculate the probability amplitudes, apply the Born rule, extract predictions, move forward. But the gap persists, and it's not a minor footnote. It concerns the most basic question one can ask. Why does anything feel like anything at all? The mathematical description of quantum systems evolves according to the Schrödinger equation, a deterministic wave equation that produces superpositions, states where a particle exists in a combination of multiple classical states simultaneously. Left undisturbed, this evolution is smooth and continuous. An electron doesn't have a definite position, but rather a spread-out wave function that assigns probability amplitudes to every possible location. 2 paths through an interferometer don't represent uncertainty about which path the particle took. The mathematics insists the particle exists in a superposition of both paths. This isn't metaphorical imprecision. The interference patterns that emerge when these paths recombine can only be explained if both paths contribute simultaneously to the particle's quantum state. The trouble begins when you try to observe which path the particle actually took. Place a detector at one of the slits and measure. Suddenly, the interference pattern vanishes. The particle is found at one slit or the other, never both. The act of measurement appears to force the system from a superposition of possibilities into a single, definite outcome. This transition from quantum superposition to classical definiteness is called wave function collapse, and nothing in the Schrödinger equation predicts or describes it. The equation only governs smooth, deterministic evolution of probability amplitudes. Collapse is something else entirely, a second rule grafted onto the theory to account for what happens when measurements occur. This dual structure creates what's known as the measurement problem. Quantum mechanics provides 2 completely different prescriptions for how physical systems evolve: unitary evolution via the Schrödinger equation when left alone, and non-unitary collapse governed by the Born rule when measured. The theory offers no principle for determining when one process ends and the other begins. There's no fundamental definition of what constitutes a measurement or why measurements should behave differently from any other physical interaction. Since measuring devices are themselves made of atoms that obey quantum mechanics, it's unclear why they should trigger collapse rather than simply becoming entangled with the system they measure, themselves entering superposition. One might assume this is merely a problem of scale, that quantum effects apply to microscopic particles, while classical physics emerges naturally at larger scales. But this assumption doesn't hold under scrutiny. There's no size threshold written into the equations where quantum mechanics stops applying. Experiments have demonstrated quantum superposition in systems containing thousands of atoms, including organic molecules with more than 800 atoms and mechanical resonators comprising trillions of atoms. These systems exhibit genuine quantum behavior, interference patterns, coherence, and superposition states. The quantum classical boundary isn't fixed by mass or complexity. Something else determines when quantum behavior gives way to classical definiteness. The mechanism that bridges this gap is called decoherence. When a quantum system interacts with its environment, the surrounding air molecules, thermal radiation, gravitational fields, these interactions rapidly entangle the system with countless environmental degrees of freedom. This entanglement doesn't destroy the superposition in an absolute sense. Rather, it spreads the quantum information across so many particles that the coherence between different components of the superposition becomes effectively unobservable. The system still exists in superposition mathematically, but the interference terms that would reveal this superposition become buried in environmental noise beyond any practical measurement capability. Decoherence timescales are extraordinarily short for macroscopic objects. A dust particle floating in space will decohere from cosmic microwave background radiation alone in less time than it takes light to cross an atom. For something the size of a cat, decoherence would occur in a time span shorter than any known physical measurement could possibly resolve. This explains why we never observe large objects in superposition states. The environment acts as a continuous measuring device, constantly collapsing quantum coherence before it can manifest at scales we can perceive. Classical reality emerges not from any fundamental change in physical law, but from the practical impossibility of isolating macroscopic systems from their environment long enough to observe their quantum nature. Yet decoherence, while solving the practical question of why we don't see quantum behavior at large scales, doesn't resolve the measurement problem itself. The mathematics of decoherence describes how superpositions become entangled with their environment, transforming pure states into mixed states that behave like classical probability distributions. But this transformation is still unitary evolution, still governed by the Schrödinger equation. The superposition doesn't disappear, it simply becomes inaccessible. The fundamental question remains, when a measurement occurs, why do we observe one definite outcome rather than experiencing the superposition itself? This is where interpretation becomes unavoidable. The equations alone don't answer this question. They describe probability amplitudes evolving in Hilbert space, but they don't explain why a particular outcome manifests in experience, or what selects that outcome from the range of possibilities encoded in the wave function. Different interpretations offer different answers, each preserving the mathematical structure while proposing distinct ontologies for what the theory describes. The Copenhagen Interpretation, historically dominant and still widely taught, treats wave function collapse as a fundamental postulate. When a measurement occurs, the wave function discontinuously collapses to a definite state corresponding to the measurement's outcome. This interpretation explicitly rejects questions about what happens before measurement or what the wave function represents between observations. It treats quantum mechanics as fundamentally about predicting measurement results rather than describing an underlying reality. The formalism works, pressing beyond it invites conceptual confusion. This pragmatic stance allowed quantum mechanics to develop as a practical theory without getting mired in philosophical disputes, but it leaves the measurement problem unaddressed by Decoherence, arguing it outside the scope of physics. The many worlds interpretation takes the opposite approach. It accepts the Schrödinger equation as the complete description of quantum evolution and rejects wave function collapse entirely. When a measurement occurs, the universe doesn't collapse to one outcome. Instead, it branches into multiple non-interacting components, each corresponding to a different possible measurement result. Every outcome occurs, but in separate branches of the universal wave function that can no longer interfere with one another. Observers split along with the universe, experiencing one branch while remaining unaware of the others. This interpretation preserves unitary evolution throughout and requires no special measurement postulate, but at the cost of accepting an enormous proliferation of parallel realities, none of which can be directly observed or verified. Objective collapse theories propose a different solution, modifying quantum mechanics itself to include a physical collapse mechanism. These theories add stochastic terms to the Schrödinger equation that become negligible for small systems, but trigger rapid collapse for large ones. The collapse isn't triggered by measurement or consciousness, but occurs spontaneously as a genuine physical process governed by new laws. The best developed versions, such as the GRW theory, predict extremely rare spontaneous collapses for individual particles, but frequent collapses for macroscopic objects due to their vast number of constituent particles. This explains why quantum superpositions persist for isolated particles, but never for CATs or measuring devices. These theories make testable predictions that differ slightly from standard quantum mechanics, though experiments haven't yet reached sufficient precision to definitively test them. Pilot wave theory, or Bohmian mechanics, adds definite particle positions to the wave function. Particles always have precise locations and velocities, while the wave function guides their motion through space. The wave function never collapses. It continues evolving deterministically even during measurements. What appears as collapse is simply the particle being guided into one branch of the wave function, while other branches become empty. This interpretation restores determinism and eliminates randomness, but requires accepting faster-than-light influences between particles and abandoning the principle that the wave function contains all physical information. The particle positions exist in addition to the wave function, adding ontological structure not present in the mathematical formalism. None of these interpretations has achieved consensus acceptance. Each preserves the empirical predictions of quantum mechanics while proposing radically different pictures of underlying reality. Copenhagen refuses to describe reality between measurements. Many worlds multiplies reality into countless parallel branches. Collapse theories modify the fundamental equations. Pilot wave theory adds hidden variables. The mathematics remains identical across all approaches, yet the ontologies are mutually incompatible. This proliferation of interpretations isn't a sign of confusion or lack of rigor. It reflects something deeper. The mathematical structure of quantum mechanics underdetermines the reality it describes. The formalism successfully predicts measurement outcomes without specifying what exists between measurements or what selects particular outcomes from quantum possibilities. What's remarkable is that this situation has persisted for nearly a century, despite quantum mechanics being the most precisely tested theory in physics. We can calculate atomic spectra to 12 decimal places, engineer quantum computers, manipulate individual atoms with exquisite control, yet we cannot agree on what the theory says about the nature of physical reality. The success of quantum mechanics as a predictive framework hasn't resolved, but has actually sharpened the interpretive crisis. Each new experimental achievement confirms the mathematical structure, while leaving the conceptual questions untouched. Part of the difficulty stems from the role observation plays in the theory's structure. Quantum mechanics treats measurement as a primitive concept without defining it in physical terms. This creates a problematic circularity. Measurements reveal properties of quantum systems, but what counts as a measurement depends on drawing a boundary between the quantum system and the classical measuring apparatus. Yet if everything is ultimately quantum, this boundary is arbitrary. Moving it doesn't change predictions. Decoherence ensures measurements at any scale yield consistent results, but it changes the interpretation of what's physically occurring. Is collapse triggered by the interaction with photons in a detector, by the amplification to a macroscopic signal, by the recording in computer memory, by the observation by a conscious experimenter? The mathematics doesn't distinguish between these possibilities. This ambiguity has led some to suggest consciousness plays a fundamental role in quantum mechanics, that awareness somehow collapses wave functions. This view lacks support in modern physics. Measurements work perfectly well with automatic detectors, computer systems, and unconscious recording devices. Decoherence occurs through any environmental interaction, regardless of whether consciousness is present. The appearance that observation affects quantum systems stems from the physical interaction required to obtain information, not from any special properties of minds or awareness. When you observe a particle's position, you must bounce photons off it, entangling the photon's state with the particle's state. This physical interaction, not the subsequent awareness of the result, is what affects the quantum system. Nevertheless, the measurement problem touches on questions about the relationship between physical description and subjective experience. Quantum mechanics describes probability amplitudes evolving in abstract mathematical spaces. Our experience presents definite outcomes: a pointer at one position, a detector clicking, a particle found here rather than there. The transition from one to the other, from quantum possibilities to classical actuality, is where the conceptual difficulty concentrates. Decoherence explains why this transition appears to occur rapidly for macroscopic systems, but it doesn't explain why we experience one outcome rather than inhabiting the superposition itself. The mathematics describes a branching structure of possibilities, but experience is singular and definite. This gap between mathematical description and lived experience isn't unique to quantum mechanics. Classical physics also describes the world in abstract mathematical terms, differential equations governing fields, and trajectories that bear little resemblance to immediate sensory experience. But classical physics at least describes a definite state of the world at each moment, with properties existing whether or not we observe them. Quantum mechanics, in its standard formulation, doesn't provide this. The wave function encodes possibilities and correlations, but not a definite state of affairs in ordinary space and time. Understanding why reality feels real despite resting on quantum foundations requires grappling with this fundamental mismatch between the theory's mathematical structure and the structure of experience. The question isn't whether quantum mechanics is correct, it demonstrably is, within its domain of applicability. The question is what it means for reality to be quantum at its base, while presenting itself as classical at the scale of human perception. Decoherence provides much of the answer by showing how classical behaviour emerges from quantum laws through environmental interaction. But it doesn't close the interpretive gap entirely. Multiple mutually inconsistent pictures of reality remain compatible with the same mathematical formalism and the same experimental predictions. This situation might seem troubling, but it also reveals something important about the relationship between physics and reality. Physical theories are mathematical structures that encode patterns in observational data. They succeed when they generate accurate predictions and fail when they don't. Quantum mechanics succeeds spectacularly by this measure, but whether a successful theory provides a complete description of reality, whether it tells us not just how systems behave, but what they fundamentally are, is a question the theory itself cannot answer. The formalism is compatible with multiple ontologies, multiple pictures of what exists. Choosing between them requires invoking criteria beyond empirical adequacy: simplicity, parsimony, explanatory power, conceptual coherence. These are philosophical rather than purely physical considerations. The measurement problem thus sits at the intersection of physics and philosophy, where mathematical precision meets interpretive ambiguity. It's a problem that arises not from incomplete physics, but from the gap between what physics describes and what exists. We have a theory that works, but we don't have a consensus story about what that theory means. And remarkably, this uncertainty doesn't prevent the theory from functioning perfectly as a tool for understanding and manipulating nature. Quantum mechanics remains the foundation of modern technology and scientific understanding, despite the unresolved questions about its interpretation. What this reveals is that reality feeling real, the immediate definiteness of experience, doesn't require a complete theory of why measurement yields definite outcomes or what exists between observations. The psychological and practical aspects of reality are robust to interpretive uncertainty about quantum foundations. We navigate a classical appearing world because decoherence rapidly destroys quantum coherence at macroscopic scales, regardless of which interpretation correctly describes what's happening at the quantum level. The stability and reliability of everyday experience emerge from quantum mechanics itself, not from any additional layer of classical physics imposed on top of it. This brings us to a deeper question. If multiple incompatible interpretations can account for the same observed phenomena, what constrains our understanding of quantum reality? The next step requires examining not just what the mathematics predicts, but what kinds of physical pictures remain logically consistent with those predictions, and what this tells us about the limits of knowledge itself when the theory that governs reality refuses to specify a unique reality to be known. The constraints imposed by quantum theory don't come from insufficient data or incomplete measurement. They emerge from the mathematical structure of the theory itself, from what the formalism can and cannot express. This creates a peculiar situation. We possess equations that predict experimental outcomes with extraordinary precision, yet those same equations refuse to specify what exists between measurements, or why definite outcomes appear when measurements occur. Consider what it means for a theory to be complete. A complete physical theory should tell us not just how systems behave, but what they are. Classical mechanics achieved this. Newton's equations described particles with definite positions and velocities existing independently of observation. The theory specified a determinate state at every moment, and measurement simply revealed that pre-existing state. Quantum mechanics breaks this pattern fundamentally. The quantum state, the wave function, doesn't describe a system possessing definite properties. It encodes probabilities for obtaining various measurement results. Before measurement, the theory doesn't say the electron is at position A or position B. It says the electron exists in a superposition of both positions, with specific amplitudes assigned to each. These amplitudes aren't epistemic. They don't represent our ignorance of which position the electron actually occupies. They're ontic features of the quantum state itself. This generates an immediate conceptual problem. If the wave function represents the complete physical state, and the wave function includes superpositions of macroscopically distinct configurations, why do measurements always yield single definite outcomes? The mathematics allows for superpositions to persist indefinitely under Schrödinger evolution. Nothing in the unitary dynamics forces a transition from superposition to single outcome. Yet that transition happens every time we perform a measurement. The Copenhagen Interpretation addressed this by introducing wave function collapse as an additional postulate. When a measurement occurs, the superposition instantaneously reduces to a single ion state corresponding to the measured value. This solves the problem of definite outcomes, but at a severe cost. Collapse isn't derived from the theory's fundamental dynamics. It's imposed as an extra rule that applies only during measurement. This creates two incompatible evolution laws: smooth Schrödinger dynamics between measurements and discontinuous collapse during measurements. The arbitrariness of this division has troubled physicists since quantum mechanics was formulated. What counts as a measurement? Does the measuring apparatus need to be macroscopic? Does it require consciousness? The Copenhagen Interpretation never provided clear answers. It simply asserted that collapse happens when measurements occur, leaving measurement as an undefined primitive concept in the theory. Hugh Everett proposed a radically different solution in 1957. His many worlds interpretation eliminates collapse entirely. The wave function never reduces. Instead, when a measurement occurs, the universe branches. Each possible outcome is realized in a separate branch of reality. The observer splits along with the universe, with each copy experiencing one definite outcome. From any observer's perspective, measurements appear to yield single results, but this appearance emerges from the branching structure rather than from actual collapse. Many worlds preserves the universality of quantum mechanics. The same Schrödinger equation governs everything, including measurement apparatus and observers. There's no special measurement postulate, no arbitrary division between quantum and classical realms. The theory describes one universal wave function evolving unitarily according to the same dynamics at all scales. Decoherence, the rapid spreading of quantum correlations into the environment, explains why different branches become effectively independent and why classical behaviour emerges at macroscopic scales. Yet many worlds faces its own conceptual challenges. The theory predicts that all possible measurement outcomes occur, but we only experience one. Why? The standard answer invokes decoherence to explain why different branches can't interfere with each other, rendering them operationally independent. But this doesn't fully explain the subjective appearance of single outcomes. From a global perspective, all branches exist. The single outcome we experience is an artifact of our location within one particular branch. The theory must explain why subjective experience selects one branch rather than perceiving the superposition of all branches. David Deutsch and others have argued that the selection happens naturally through decoherence. Once an observer becomes entangled with a measurement's outcome, they become part of a specific branch. The observer in that branch can only access information consistent with their branch. But this explanation involves subtle reasoning about the relationship between physical states and subjective experience. It requires accepting that the observer genuinely splits with each copy being equally real, even though any given copy perceives only one outcome. Some physicists find this ontological cost too high. The theory multiplies entities lavishly. Every quantum measurement anywhere in the universe generates new branches, exponentially proliferating worlds. Occam's razor traditionally favours simpler explanations, and many worlds seems anything but simple. Defenders counter that the theory's fundamental postulates are actually minimal, just the Schrödinger equation, with no additional collapse mechanism. The proliferation of branches is a consequence, not an assumption. But whether this proliferation represents genuine ontological simplicity remains disputed. Bohmian Mechanics offers a third approach. It retains particles with definite positions at all times, restoring the determinism and realism of classical physics. The wave function still exists in this theory, but it plays a different role. Rather than representing the complete physical state, it guides the motion of particles through a quantum potential. The theory reproduces all quantum predictions, while maintaining that particles always have definite locations, even when not measured. This restoration of classical intuition comes with trade-offs. Bohmian mechanics is explicitly non-local. The quantum potential influencing one particle's motion depends instantaneously on the positions of all other particles, regardless of spatial separation. This doesn't violate relativity's prohibition on faster-than-light signaling. The non-local effects can't be used to transmit information, but it does violate the spirit of locality that physics has traditionally embraced. Effects in one region depend on distant events, without any mediating influence propagating between them. Additionally, Bohmian mechanics treats the wave function as physically real. It exists in a high-dimensional configuration space rather than ordinary three-dimensional space. A system of n particles has a wave function living in a 3n dimensional space. This raises questions about the ontological status of configuration space. Is it physically real or merely a mathematical tool? If real, how does it relate to the three-dimensional space we perceive? These questions complicate what initially seems like a straightforward restoration of classical realism. Objective collapse theories take yet another direction. Rather than accepting indefinite superpositions at all scales or multiplying worlds, these theories modify quantum mechanics itself. They add stochastic collapse terms to the Schrödinger equation, causing wave functions to spontaneously localize. For microscopic systems, these modifications are negligible, and quantum mechanics remains essentially unchanged. For macroscopic systems, the collapse rate increases dramatically, preventing superpositions from persisting at large scales. The GRW theory, proposed by Ghirardi, Rimini, and Weber, exemplifies this approach. It adds random, spontaneous localization events to the wave function's evolution. Each particle undergoes localization with extremely low probability, roughly once per 100 million years. For a single particle, this is undetectable, but macroscopic objects contain enormous numbers of particles. The probability that at least one particle localizes becomes very high, and when one particle localizes, it collapses the entire system's wave function through entanglement. This mechanism provides a natural boundary between quantum and classical behavior. Microscopic systems remain quantum because localization is rare. Macroscopic systems behave classically because localization is frequent. The theory explains why we don't observe superpositions of cats or chairs without invoking consciousness or measurement as special. Classical behavior emerges from an objective physical process built into the theory's dynamics. However, objective collapse theories face empirical challenges. The collapse mechanism must be strong enough to suppress macroscopic superpositions, but weak enough to avoid conflict with existing quantum experiments. Finding parameters that satisfy both constraints has proven difficult. Moreover, these theories predict slight deviations from standard quantum mechanics in precision experiments. So far, such deviations haven't been observed, constraining the parameter space available to collapse theories. Future experiments may either detect these deviations, supporting collapse theories, or further restrict the viable parameter space, potentially ruling them out. The proliferation of interpretations reveals something important about quantum mechanics. The theory's mathematical structure underdetermines its physical meaning. Multiple incompatible ontologies can account for the same experimental predictions. This isn't a temporary situation, reflecting incomplete development of the theory. It's a fundamental feature arising from the theory's structure. Quantum mechanics predicts probabilities for measurement outcomes. It doesn't predict what exists between measurements or why particular outcomes occur. Different interpretations fill this explanatory gap differently, by adding collapse, by multiplying worlds, by introducing hidden variables, or by modifying the dynamics. But the empirical content remains identical across interpretations. They make the same experimental predictions while telling radically different stories about reality. This situation has philosophical implications beyond physics. It demonstrates that empirical adequacy, successfully predicting observations, doesn't uniquely determine ontology. Multiple incompatible pictures of what exists can be empirically equivalent. Choosing between them requires invoking criteria beyond predictive success: theoretical simplicity, conceptual clarity, compatibility with other theories, or aesthetic preference. These considerations are legitimate, but they're not purely empirical. They involve judgments about what makes a theory explanatorily satisfying. Some physicists conclude from this that interpretation questions are meaningless, that physics should restrict itself to predicting observations without speculating about underlying reality. This instrumentalist stance has practical appeal. If interpretations make identical predictions, why worry about which is correct? Just use the theory to calculate and don't ask what it means. Yet this response seems unsatisfying when applied to quantum mechanics specifically. The theory doesn't just predict observations, it describes the fundamental structure of reality. Everything we know about physics indicates that quantum mechanics governs all physical systems. If we refuse to interpret the theory, we're refusing to say what exists. We're treating the most fundamental description of nature as merely a calculation tool while remaining agnostic about reality itself. Moreover, interpretation questions aren't purely academic. They influence how physicists think about quantum mechanics, what problems seem important, and what research directions seem promising. The development of quantum information theory was partly motivated by taking quantum states seriously as physical entities rather than mere calculational devices. Quantum computing exploits superposition and entanglement, features that only make sense given some interpretation of what quantum states represent. The measurement problem sits at the intersection of physics and metaphysics. The physics is clear. Quantum mechanics makes accurate predictions. The metaphysics is murky. What those predictions tell us about reality remains contested. This murky metaphysics isn't peripheral to physics. It concerns the nature of physical states, the relationship between mathematics and reality, and what counts as a complete physical theory. Perhaps the most unsettling aspect is that this situation might be permanent. We might never have empirical grounds for choosing between interpretations. The many worlds interpretation, Bohmian mechanics, and suitably modified collapse theories could remain empirically indistinguishable indefinitely. If so, the question, what does quantum mechanics tell us about reality, may not have a unique answer determinable by physics alone. This doesn't make the question meaningless. It means the answer involves both empirical and conceptual considerations. Physics provides the mathematical structure and experimental constraints. Philosophy evaluates how different interpretations handle that structure and what conceptual costs they incur. The final judgment involves weighing these considerations against each other, a process that isn't purely empirical, but isn't purely arbitrary either. What emerges is a picture of physics as inherently underdetermined by observation. The theory that most accurately describes reality, quantum mechanics, admits multiple incompatible interpretations. This underdetermination isn't a flaw to be corrected. It's a structural feature arising from the relationship between mathematical formalism and physical ontology. The formalism constrains what can be said about reality, but it doesn't uniquely specify what reality is. This conclusion challenges the traditional view of physics as progressively revealing objective reality through empirical investigation. That view assumes observation can eventually distinguish between competing descriptions. But when competing descriptions make identical empirical predictions, observation can't adjudicate between them. The choice becomes underdetermined, requiring philosophical reasoning beyond empirical test. For the question of why reality feels real, this means there may be no single physical answer. Different interpretations explain the definiteness of experience differently. Copenhagen invokes collapse. Many worlds invokes branching. Bohmian mechanics invokes hidden variables. Collapse theories invoke spontaneous localization. Each explanation works within its interpretive framework. None can be empirically proven superior. What physics establishes is that quantum mechanics, however interpreted, generates classical appearing behavior at macroscopic scales through decoherence. The rapid destruction of quantum coherence by environmental interaction explains why we don't observe superpositions of everyday objects. This much is interpretation independent. It's a consequence of the quantum dynamics themselves, not of any particular interpretive choice, but why decoherence produces subjective experiences of definite outcomes rather than awareness of superposition remains interpretation dependent. Each interpretation offers an account, but physics alone can't determine which account correctly describes what happens. The gap between physical description and experiential reality persists across all interpretations, though each interprets the gap differently. This leaves us with an uncomfortable recognition. The most fundamental physical theory we possess doesn't uniquely specify what reality is. It provides a mathematical structure that successfully predicts observations while remaining compatible with multiple ontologies. The definiteness of experience, the fact that reality feels real, emerges somehow from this structure. but exactly how it emerges and what exists to give rise to that emergence remains genuinely unclear. The mathematics works perfectly. Physicists can calculate the probability that a particle will be detected at a specific location with remarkable precision. They can predict the behavior of atoms in molecules, the properties of materials, the outcomes of particle collisions. The equations generate numbers that match experimental results to extraordinary accuracy. Yet those same equations describe a reality fundamentally unlike the one we inhabit, a reality of superposed states, indefinite properties, and observer-dependent outcomes. Between the mathematics and the experience lies a conceptual chasm that remains unbridged. Consider what quantum mechanics actually says about a particle before it's measured. The theory describes it not as having a definite position that we simply don't know, but as genuinely existing in a superposition of many possible positions simultaneously. This isn't ignorance about where the particle is. It's a claim about what the particle is, a spread out wave of probability rather than a localized point. The mathematics insists on this interpretation. The Schrödinger equation, which governs how quantum states evolve, is linear. Linearity means that if a particle can be in state A or state B, it can also be in a state that combines both. Not either A or B, but we don't know which. Actually both, simultaneously, in a coherent quantum superposition. This mathematical structure has been tested exhaustively. Interference experiments demonstrate that particles really do explore multiple paths at once. The patterns produced can only be explained if the particle somehow interacts with itself across different possible trajectories. The mathematics isn't just a computational tool, it accurately describes something genuine about how nature behaves at the quantum level. The predictions derived from treating particles as superpositions work. The predictions derived from treating them as having definite but unknown properties fail. Yet when we perform a measurement, we never observe a superposition. We always get a single, definite result. The particle is detected at one location, not multiple locations simultaneously. Its spin points in one direction, not several. The measurement yields a number, a specific outcome selected from the range of possibilities the superposition encompassed. The mathematical description of what happens during measurement is radically different from the description of what happens between measurements. The smooth deterministic evolution governed by Schrödinger's equation gets replaced by something else, a discontinuous jump to a definite state with the probability of each outcome given by the Born rule. This dual description creates an immediate problem. If quantum mechanics is universal, if it describes all physical systems, then measuring devices are themselves quantum systems. They should evolve according to the Schrödinger equation. But the Schrödinger equation predicts that when a measuring device interacts with a quantum system in superposition, the device itself enters a superposition of having measured different outcomes. The measurement doesn't collapse the superposition, it spreads it. The combined system of particle and detector becomes entangled, with the detector's state correlated to the particle's state, but both remaining in superposition. This is where the mathematical description diverges most starkly from experience. The mathematics says the measuring device should be in a superposition of pointer positions, simultaneously showing different readings. We never observe this. We see one reading. The device appears to have one definite state, not a combination of states. Something about the process of measurement produces a single outcome from multiple possibilities. Yet that process isn't captured, by the standard quantum evolution. One might think this just reflects our ignorance, that the device really does have a definite state, and we simply don't know which until we look. But that interpretation fails. Quantum mechanics has been tested against theories that assume definite but hidden properties, and those theories make different predictions. Bell's theorem, combined with decades of experimental tests, demonstrates that no theory assigning definite properties to particles before measurement can reproduce quantum mechanical predictions unless it allows for instantaneous influences across arbitrary distances. The universe doesn't behave as if particles have definite properties we're merely ignorant of. It behaves as if those properties genuinely don't exist until they're measured. This creates a conceptual problem rather than an empirical one. The mathematics accurately predicts what we observe. The issue is understanding what that mathematics describes. What physical process corresponds to the selection of a single outcome from a superposition? Where and when does this selection occur? Does it happen in the measuring device, in the observer's consciousness, nowhere at all? The equations work, but their relationship to physical reality remains unclear. Decoherence provides crucial insight here, though not a complete solution. When a quantum system interacts with its environment, which includes everything from air molecules to electromagnetic radiation, the delicate phase relationships that enable quantum superposition become scrambled and dispersed throughout the environment. This happens extraordinarily rapidly for any macroscopic object. The timescales for decoherence of everyday objects are measured in fractions of a second, so small they're effectively instantaneous. A dust particle in space decoheres in less than a millisecond due to interactions with the cosmic microwave background. A protein molecule in solution decoheres essentially instantly. Decoherence explains why we don't observe macroscopic superpositions. The quantum coherence that would be required for a measuring device or a cat to display superposition behavior gets destroyed before any measurement could detect it. The information about the quantum state gets irreversibly scattered into the environment, making it practically impossible to recover and observe interference effects. From the perspective of any observer embedded in the environment, the system appears to have collapsed to a definite state. The superposition hasn't truly disappeared. It's become entangled with an enormous environment of particles and fields, but it's no longer observable by any local measurement. This provides a physical mechanism for the emergence of apparent classicality from quantum laws. Decoherence shows how quantum mechanics itself generates the appearance of definite outcomes without requiring any additional collapse postulate. The mathematics of quantum evolution, when applied to systems interacting with complex environments, naturally produces the statistical mixtures that characterize classical probability rather than quantum superposition. We don't see superpositions of macroscopic objects because environmental interaction destroys the phase relationships necessary for superposition faster than we could possibly measure them. But decoherence doesn't solve the measurement problem completely. It explains why superpositions become unobservable, but not why we experience one outcome rather than another. The mathematics still describes all outcomes as occurring. They're just spread across different branches of the entangled state. From a global perspective, the superposition persists. It's only from the local perspective of an observer embedded in one branch that a single outcome appears to have occurred. Decoherence explains the appearance of collapse, not collapse itself. This is where interpretation becomes necessary. The mathematical formalism of quantum mechanics generates accurate predictions, but doesn't uniquely specify what exists. Different interpretations offer different accounts of what happens during measurement, and these accounts remain empirically indistinguishable. The Copenhagen Interpretation posits genuine collapse. The superposition actually reduces to a single outcome, with the probability of each outcome given by the Born rule. But this interpretation doesn't explain what triggers collapse or what physical process implements it. It treats collapse as a fundamental dynamical process without providing a mechanism. The many worlds interpretation avoids collapse entirely. It takes the mathematics completely literally and says that all outcomes occur. When a measurement happens, the universe branches into multiple versions, with each version containing an observer who experienced a different outcome. There's no collapse, just an ever-proliferating tree of branching realities. We experience one outcome because we exist in one branch, but all outcomes are equally real in other branches. The appearance of collapse emerges from the subjective perspective of observers who can only access their local branch after decoherence has made the branches effectively independent. Bohmian Mechanics adds hidden variables, actual particle positions that exist even when unmeasured. The wave function guides these particles, but the particles have definite locations at all times. Measurement reveals pre-existing properties rather than creating them. The superposition in the wave function doesn't correspond to the particle being in multiple places. It describes the probability current that guides where the particle moves. This interpretation makes different ontological claims. It says particles have definite positions while making identical empirical predictions. Objective collapse theories modify quantum mechanics itself, adding terms to the Schrödinger equation that cause spontaneous collapse. These collapses happen randomly and extremely rarely for individual particles, so they don't affect microscopic physics. But the collapse rate scales with mass or complexity, meaning macroscopic objects collapse rapidly to definite states. These theories make slightly different predictions than standard quantum mechanics, predictions that might eventually be testable, but current experiments can't distinguish them. Each interpretation handles the measurement problem differently, yet all remain compatible with the mathematical formalism and experimental results. This isn't a temporary situation awaiting resolution through better experiments. The interpretations may be permanently empirically indistinguishable. They make identical predictions for all observable quantities while offering incompatible accounts of what exists. The mathematics constrains what can be said about reality, but doesn't uniquely determine what reality is. This leaves the question of why reality feels real in a peculiar position. The feeling of definiteness, the experience of the world as having actual properties rather than existing in superposition, can be explained within any interpretation. Copenhagen says, superpositions collapse to definite states. Many worlds says we experience one branch while others exist unseen. Bohmian Mechanics says particles always had definite positions. Collapse theories say spontaneous localization produces definiteness. Each explanation works within its framework. None can be empirically proven superior. What physics establishes is that quantum mechanics, however interpreted, generates classical behavior through decoherence. The rapid destruction of quantum coherence by environmental interaction explains why macroscopic objects appear definite. This is interpretation independent, a consequence of quantum dynamics itself. But why decoherence produces subjective experiences of definite outcomes rather than awareness of superposition remains interpretation dependent. The gap persists because the mathematics describes systems from the outside, as configurations of particles and fields evolving according to equations. Subjective experience describes reality from the inside, as a stream of definite perceptions and events. The mathematical description doesn't include phenomenological terms. It doesn't reference what things feel like, or what it's like to be an observer. The equations describe correlations between physical states, but not the qualitative character of those states as experienced. This isn't a flaw in quantum mechanics. The theory wasn't designed to explain consciousness or subjective experience. It was designed to predict measurement outcomes, and it does this extraordinarily well. But the question of why those measurement outcomes feel like anything at all, why there's something it's like to observe a definite result rather than merely existing in a correlated state, lies outside the theory's scope. Some physicists argue this gap doesn't require explanation. Subjective experience is just what certain physical processes feel like from the inside. When particles in a brain enter states correlated with environmental conditions, the resulting configuration simply is an experience. The feeling of definiteness arises from the physical fact of decoherence having destroyed quantum coherence, leaving the brain in a state that classically represents one outcome. No additional explanation is needed. Others find this unsatisfying. If all outcomes occur in the many worlds framework, why do we experience only one? What selects which branch contains our subjective experience? The mathematical state encompasses all branches equally. The feeling of being in one specific branch, of having witnessed one particular outcome, seems to require something beyond the mathematics. The wave function doesn't specify which term corresponds to my experience. This touches on deeper questions about the relationship between physical description and phenomenological reality. Mathematics describes structure, relationships, correlations, patterns. Experience has qualities, redness, pain, the feeling of certainty. The connection between structure and quality remains unclear. A complete description of brain states in terms of particle positions and fields wouldn't obviously include what those states feel like. The qualitative aspect seems irreducible to mathematical structure. Quantum mechanics makes this tension explicit by providing a complete mathematical description that generates accurate predictions while leaving aspects of reality underspecified. The mathematics works perfectly, but doesn't uniquely determine what exists or why it feels like anything. This isn't a problem to solve through better mathematics. It's a conceptual gap between two ways of describing reality, the mathematical and the experiential, that may not be fully bridgeable. The result is an uncomfortable pluralism. Multiple interpretations of quantum mechanics remain viable, each offering different ontological pictures. The mathematics constrains these pictures, but doesn't select among them. Empirical evidence can't adjudicate because the interpretations make identical predictions. The choice involves philosophical considerations about parsimony, naturalness, and conceptual coherence, rather than purely empirical grounds. This doesn't make the question meaningless. It means physics alone can't answer it. The mathematical formalism and experimental results are fixed. How to understand what that formalism describes, what exists, how measurements work, why we experience definite outcomes, requires interpretation. These interpretive choices involve both empirical and conceptual considerations. Physics provides the mathematical structure and experimental constraints. Philosophy evaluates how different interpretations handle that structure and what conceptual costs they incur. The question of why reality feels real thus remains genuinely open. Decoherence explains why we don't observe macroscopic superpositions. Quantum mechanics predicts measurement outcomes with extraordinary accuracy, but the relationship between the mathematics and the subjective experience of definiteness remains unresolved. Different interpretations offer different accounts, none empirically distinguishable. The feeling of inhabiting a definite world emerges somehow from quantum laws, but exactly how depends on interpretive choices that physics alone cannot determine. The mathematical structure describes outcomes, and it does this extraordinarily well. But the question of why those measurement outcomes feel like anything at all, why there's something it's like to observe a definite result rather than merely existing in a correlated state, lies outside the theory's scope. Some physicists argue this gap doesn't require explanation. Subjective experience is just what certain physical processes feel like from the inside. When particles in a brain enter states correlated with environmental conditions, the resulting configuration simply is an experience. The feeling of definiteness arises from the physical fact of decoherence, having destroyed quantum coherence, leaving the brain in a state that classically represents one outcome. No additional explanation is needed. Others find this unsatisfying. If all outcomes occur in the many worlds framework, why do we experience only one? What selects which branch contains our subjective experience? The mathematical state encompasses all branches equally. The feeling of being in one specific branch, of having witnessed one particular outcome, seems to require something beyond the mathematics. The wave function doesn't specify which term corresponds to my experience. This touches on deeper questions about the relationship between physical description and phenomenological reality. Mathematics describes structure, relationships, correlations, patterns. Experience has qualities, redness, pain, the feeling of certainty. The connection between structure and quality remains unclear. A complete description of brain states in terms of particle positions and fields wouldn't obviously include what those states feel like. The qualitative aspect seems irreducible to mathematical structure. Quantum mechanics makes this tension explicit by providing a complete mathematical description that generates accurate predictions while leaving aspects of reality underspecified. The mathematics works perfectly, but doesn't uniquely determine what exists or why it feels like anything. This isn't a problem to solve through better mathematics. It's a conceptual gap between two ways of describing reality, the mathematical and the experiential, that may not be fully bridgeable. The result is an uncomfortable pluralism. Multiple interpretations of quantum mechanics remain viable, each offering different ontological pictures. The mathematics constrains these pictures, but doesn't select among them. Empirical evidence can't adjudicate because the interpretations make identical predictions. The choice involves philosophical considerations about parsimony, naturalness, and conceptual coherence, rather than purely empirical grounds. This doesn't make the question meaningless. It means physics alone can't answer it. The mathematical formalism and experimental results are fixed. How to understand what that formalism describes, what exists, how measurements work, why we experience definite outcomes requires interpretation. These interpretive choices involve both empirical and conceptual considerations. Physics provides the mathematical structure and experimental constraints. Philosophy evaluates how different interpretations handle that structure and what conceptual costs they incur. The question of why reality feels real thus remains genuinely open. Decoherence explains why we don't observe macroscopic superpositions. Quantum mechanics predicts measurement outcomes with extraordinary accuracy. But the relationship between the mathematics and the subjective experience of definiteness remains unresolved. Different interpretations offer different accounts, none empirically distinguishable. The feeling of inhabiting a definite world emerges somehow from quantum laws, but exactly how depends on interpretive choices that physics alone cannot determine. Consider what this means for the nature of explanation itself. Physics traditionally aims to reduce complex phenomena to simpler underlying principles. Temperature reduces to molecular motion. Light reduces to electromagnetic waves. Chemical bonds reduce to electron sharing. Each reduction provides understanding by showing how apparent complexity arises from simpler components following basic rules. The relationship between quantum mechanics and classical reality doesn't fit this pattern cleanly. We have the underlying rules, the Schrödinger equation, the Born rule for probabilities, decoherence dynamics. We can calculate how these rules generate classical-looking behavior at macroscopic scales. Yet something about the explanation feels incomplete. The calculation shows that classical physics emerges as an approximation, but it doesn't explain why that approximation feels like the only reality from inside a decohered branch. This peculiarity stems from the fact that we're part of the system being described. When studying molecular motion, to understand temperature, we stand outside the system. We can observe molecules without being made of the specific molecules under study. But when studying consciousness or subjective experience, we can't step outside. We're made of quantum systems trying to understand how quantum systems give rise to the experience of definiteness that we're currently having. This creates what some philosophers call an epistemic limitation, a boundary on what we can know based on our position within reality. The mathematics of quantum mechanics may be complete as a predictive tool, while remaining necessarily incomplete as an explanation of why that mathematics corresponds to experience. We can describe the correlations between brain states and environmental conditions. We can calculate decoherence rates. We can predict measurement outcomes. But the transition from correlation to experience, from mathematical description to phenomenological reality, may lie beyond what physical theory can address. Some researchers propose that understanding this transition requires expanding physics itself. Perhaps consciousness is a fundamental aspect of reality, not reducible to particle interactions. Perhaps the laws of physics are incomplete, missing principles that govern the emergence of subjective experience. Perhaps there are aspects of reality that mathematical description fundamentally cannot capture. These proposals remain speculative and controversial. They suggest that the current formalism of quantum mechanics, while empirically successful, points towards something deeper that we haven't yet conceptualized. The measurement problem would then be a symptom of this incompleteness, a place where our current framework reaches its limits and something new is required. Other researchers argue that no expansion is needed. The mathematics is complete. The feeling that something is missing reflects our psychological difficulty accepting certain features of reality rather than any actual gap in the physics. We expect reality to match our intuitions about separateness, definiteness, and objective existence. When quantum mechanics violates those intuitions, we interpret this as a problem with the theory rather than with our intuitions. From this perspective, the measurement problem is solved. Decoherence explains why superpositions become effectively classical. Different interpretations describe what happens to the full quantum state, but they all make the same predictions. The remaining questions are philosophical, matters of how to think about the mathematics, rather than what the mathematics predicts. Physics has done its job. The feeling of incompleteness stems from expecting physics to answer questions that lie outside its domain. This debate reflects a fundamental uncertainty about the scope of scientific explanation. Should physics aim only to predict observations, or should it also explain why those observations occur? Should it describe only structure and behaviour, or should it also account for the qualitative character of experience? Different answers to these questions lead to different assessments of whether the measurement problem is solved or remains open. The practical consequences of this uncertainty are limited. For building quantum computers, the interpretive questions don't matter. Decoherence sets the constraints. For predicting experimental outcomes, different interpretations give identical results. For applications of quantum mechanics in chemistry, materials science, or particle physics, the philosophical disputes are irrelevant. The mathematics works regardless of how we interpret it, yet the conceptual consequences are profound. How we understand the relationship between quantum mechanics and classical reality shapes how we think about the nature of existence itself. Are there many worlds or one? Is consciousness fundamental or emergent? Does reality exist independently of observation? These questions connect to ancient philosophical problems about the nature of being, knowledge, and experience. The measurement problem thus occupies a strange position. It's both solved and unsolved, depending on what counts as a solution. The physics is clear. Decoherence explains the emergence of classical behaviour from quantum laws. But the metaphysics remains contested. What that emergence means for the nature of reality depends on interpretive choices that empirical evidence alone cannot determine. This situation is uncomfortable for physics, which typically values definite answers. The existence of multiple viable interpretations suggests either that the question hasn't been properly formulated or that it transcends what physics can answer. Some physicists embrace this ambiguity as a feature rather than a bug. Others see it as a temporary state that better theories will eventually resolve. The lack of consensus after nearly a century of work suggests that resolution won't come easily. The mathematical formalism has been refined extensively. Decoherence theory has been developed in detail. Experimental tests have been performed with increasing precision. Yet the interpretive questions remain as open as ever. New interpretations continue to be proposed, and old ones continue to be defended. The physicist N. David Mermin observed that new interpretations appear every year, but none ever disappear. This persistence of disagreement points to something fundamental about the question itself. It may be that quantum mechanics describes reality in a way that inherently admits multiple equally valid interpretations. The mathematics constrains what can be said, but doesn't uniquely determine ontology. Multiple pictures of what exists can reproduce the same empirical predictions, and no experiment can distinguish between them. If this is correct, then the question, what really happens during measurement? ICE may not have a single answer. Different frameworks provide different answers, all consistent with the mathematics and all empirically adequate. The choice between them involves considerations beyond empirical adequacy: simplicity, naturalness, conceptual coherence, consistency with other theories. These considerations matter, but they don't provide decisive resolution. This doesn't reduce the question to mere preference or convention. The interpretations differ in substantive ways about what exists and how reality is structured. Many worlds says all outcomes occur. Copenhagen-style approaches say only one occurs. Bohm's theory adds hidden variables. GRW theory modifies the equations. These are genuine disagreements about the nature of reality, not just different languages for describing the same thing. Yet empirical evidence alone cannot resolve these disagreements. This creates an unusual situation where physics generates a precisely defined question that physics itself cannot definitively answer. The mathematics is fixed. The experimental results are clear, but moving from mathematics to metaphysics requires interpretive steps that aren't uniquely determined by the physics. Some philosophers argue this shows that metaphysics retains an essential role, even in fundamental physics. The empirical success of quantum mechanics doesn't by itself tell us what the theory means, or what it says about reality. Those questions require philosophical analysis, in addition to mathematical calculation and experimental measurement. Physics provides the constraints, but philosophy evaluates how different interpretations satisfy those constraints and what conceptual costs they incur. This collaboration between physics and philosophy isn't a failure of physics to be complete. It reflects the nature of the questions being asked. Questions about what exists, how existence relates to description, and why mathematical structure corresponds to experience lie at the boundary between physics and philosophy. Neither discipline alone can fully address them. The measurement problem sits precisely at this boundary, requiring both physical understanding of quantum mechanics and philosophical analysis of what that understanding implies. The result is that the question of why reality feels real remains genuinely open nearly a century after quantum mechanics was formulated. We have precise mathematics. We have experimental confirmation. We have detailed understanding of decoherence. Yet we don't have consensus on what this all means for the nature of reality and experience. Different interpretations offer different answers, none empirically distinguishable, all conceptually coherent in their own terms. This openness is unsettling, but also revealing. It shows that even our most successful physical theories contain elements that resist complete explanation in purely physical terms. The mathematics describes correlations and predicts observations with extraordinary accuracy. But the relationship between that mathematical description and the experienced reality it describes involves aspects that may lie beyond what physics alone can capture. Whether this reflects a limitation of current theories or a fundamental boundary of physical explanation remains itself an open question. The persistence of this conceptual tension suggests something deeper than incomplete knowledge. Quantum mechanics works. The predictions match experiment to extraordinary precision, yet the theory itself contains no mechanism that explains why we experience definite outcomes rather than superpositions. This isn't a gap that can be filled by more precise measurements or better mathematical techniques. It's a structural feature of how the theory relates to experience. Consider what it would mean to actually resolve this question. A satisfactory answer would need to explain not just why we see definite outcomes, decoherence addresses that, but why there are perspectives at all. Why does the mathematical structure give rise to experiential states? Why does it feel like something to be a pattern of quantum correlations embedded in an environment? These questions don't admit purely physical answers because they ask about the relationship between physical description and subjective experience. Some argue this relationship is itself physical, that consciousness emerges from complex information processing, that experience reduces to neural activity, that the gap between description and experience will eventually close as neuroscience advances. This materialist position is coherent and may be correct, but it doesn't eliminate the conceptual puzzle. Even if we perfectly map brain states to experiential states, we're still describing correlations between physical processes and subjective experiences. The correlation itself remains unexplained. Others suggest the relationship runs the opposite direction, that consciousness is fundamental and physical reality emerges from it. This idealist position also has defenders and its own internal logic, but it faces the opposite problem, explaining why subjective experience takes the specific forms it does, why it obeys mathematical laws, why different observers agree on measurement outcomes despite having separate experiential streams. The measurement problem sits at the intersection of these philosophical traditions, forcing both to confront their limits. Neither pure materialism nor pure idealism fully accounts for the strange relationship between quantum mechanics and experience. The mathematics describes correlations with perfect accuracy, but says nothing about why those correlations feel like anything at all. Experience presents itself as immediate and undeniable, but offers no window into why it should correspond to specific physical states. This impasse suggests the question may not be answerable within current conceptual frameworks. Perhaps the relationship between physical law and subjective experience represents a fundamental aspect of reality that can't be reduced to either side. Perhaps consciousness and physical process are two aspects of something more basic that our concepts can't yet capture. Or perhaps the question itself is malformed, asking for something that doesn't exist, a bridge between incommensurable domains. The practical consequences of this uncertainty are already visible in quantum technology. Quantum computers exploit superposition to perform certain calculations exponentially faster than classical machines. But maintaining superposition requires extreme isolation from the environment. The moment quantum information interacts with the outside world, decoherence destroys the computational advantage. Engineers fight decoherence through cryogenic cooling, electromagnetic shielding, and error correction codes. But these are temporary measures, not solutions to the fundamental problem. The same pattern appears in quantum communication, quantum sensing, and quantum metrology. All these technologies push against the boundary where quantum behavior gives way to classical definiteness. All of them require extraordinary effort to maintain quantum coherence long enough to extract useful information. The difficulty isn't merely technical, it reflects something fundamental about how quantum systems interact with macroscopic environments, the same interaction that produces definite measurement outcomes. This suggests a deep connection between the measurement problem and the limits of quantum technology. The reason we can't build room temperature quantum computers may be intimately related to the reason we experience definite outcomes rather than superpositions. Both phenomena emerge from the same physical process, entanglement with complex environments. Understanding one might illuminate the other, but even perfect understanding of decoherence wouldn't resolve the measurement problem's philosophical dimension. We might learn to control quantum coherence with arbitrary precision, building quantum technologies that work reliably at all scales. We might map every detail of how environmental interaction destroys superposition. Yet the question of why this process produces subjective experiences of definite outcomes would remain. The explanatory gap between physical process and phenomenal experience doesn't close through better engineering or more detailed mathematical models. Some physicists argue this shows the measurement problem isn't really a physics problem at all. Physics describes correlations between observables. It predicts measurement outcomes. It doesn't, and perhaps shouldn't, explain why those outcomes feel like anything. Questions about subjective experience belong to philosophy or cognitive science, not fundamental physics. This position has merit. It respects the scope and methods of physics, while acknowledging limits to what physical theory can address. But this disciplinary boundary doesn't eliminate the puzzle. Even if physics properly restricts itself to describing correlations, someone must still explain the relationship between those correlations and experience. If physics can't do this, what can? Philosophy offers conceptual analysis but not empirical purchase. Neuroscience maps brain activity but doesn't bridge the explanatory gap. The question doesn't fit neatly into any existing discipline. This interdisciplinary character may be essential rather than incidental. Questions about the relationship between physical law and subjective experience require both physical understanding and philosophical analysis. Neither alone suffices. Physics provides the constraints, the mathematical structure, the experimental results, the theoretical framework. Philosophy examines how different interpretations satisfy those constraints and what conceptual costs they incur. The measurement problem demands this collaboration, yet even joint effort hasn't produced consensus. After nearly a century of analysis, multiple interpretations remain viable. Each has defenders who find it conceptually satisfying. Each faces objections from those who prefer alternatives. No empirical test can distinguish between them. This persistence of multiple interpretations isn't a failure of analysis. It may reflect genuine underdetermination, the possibility that the question admits multiple equally valid answers. If so, this represents something unusual in physics. Most physical questions eventually yield to decisive evidence or mathematical insight. Disagreements persist about details, but consensus emerges on fundamentals. The measurement problem resists this pattern. The fundamentals remain contested. The most basic question, what actually happens during measurement, has no agreed answer. This might indicate that what actually happens isn't the right question. Perhaps the measurement problem asks for something physics can't provide. A story about reality that satisfies both mathematical rigor and phenomenological intuition. Mathematics demands precise, consistent, empirically testable structures. Phenomenology demands accounts that respect the immediate character of experience. These requirements may be impossible to satisfy simultaneously. Consider an analogy from mathematics itself. Gödel's incompleteness theorems prove that any sufficiently complex formal system contains true statements that can't be proved within the system. The statements are genuinely true, other methods can verify them, but the system's own rules can't establish their truth. This creates a permanent gap between truth and provability. Perhaps something similar holds for the measurement problem. Perhaps there are facts about the relationship between quantum mechanics and experience that are true, but can't be established through physical reasoning alone. The facts might be accessible through other modes of understanding: philosophical analysis, phenomenological investigation, perhaps future frameworks we haven't developed. But physics by itself, working within its proper scope and methods, may not be able to capture them. This doesn't make physics incomplete in any problematic sense. Mathematical systems are incomplete in Gödel's sense, but remain perfectly functional for their intended purposes. Similarly, physics might be unable to fully explain the measurement problem while remaining complete for its actual domain, describing the mathematical structure of physical correlations and predicting experimental outcomes. The question then becomes, what additional framework could address the aspects physics leaves untouched? What mode of understanding could bridge the explanatory gap between physical process and subjective experience? This is where current knowledge reaches its limit. Various proposals exist: integrated information theory, neutral monism, panpsychism, emergent dualism, but none has achieved the kind of empirical and theoretical success that would establish it as correct. Each proposal makes progress on certain aspects, while facing difficulties with others. Integrated information theory offers a mathematical framework for quantifying consciousness, but struggles to explain why specific integration patterns produce specific experiences. Neutral monism avoids the mind-body problem by positing a common substance underlying both, but offers little guidance about what that substance might be. Panpsychism attributes consciousness to fundamental physical entities, but faces the combination problem. How do micro-experiences combine into macro-experiences? These aren't merely technical difficulties that better theory will eventually overcome. They reflect deep conceptual challenges about how to relate physical description to phenomenal experience. The challenges persist across different theoretical frameworks, suggesting they stem from something fundamental about the problem rather than inadequacies in specific approaches. What remains clear is that reality feels real despite, or perhaps because of, these unresolved questions. The definiteness of experience, the stability of perceived objects, the continuity of conscious awareness, these features persist whether we understand them or not. The measurement problem doesn't threaten the reliability of experience, it questions our ability to explain that reliability in purely physical terms. This epistemic humility may be the appropriate attitude. Nearly a century of brilliant work by exceptional physicists and philosophers hasn't resolved the measurement problem. Multiple interpretations remain viable. Fundamental questions about the nature of measurement, the role of observers, and the relationship between quantum mechanics and experience remain open. This persistence suggests the problem may lie at the boundaries of what current frameworks can address. Perhaps future developments will provide clarity. New experimental techniques might distinguish between interpretations currently considered empirically equivalent. Novel mathematical frameworks might reveal structures that illuminate the relationship between quantum mechanics and experience. Advances in neuroscience might explain how physical processes give rise to subjective states in ways that satisfy both scientific rigor and phenomenological adequacy. Or perhaps the measurement problem will persist indefinitely, marking a permanent boundary in human understanding. Perhaps the relationship between physical law and subjective experience represents something genuinely beyond the reach of either physics or philosophy alone. Perhaps multiple interpretations will remain viable because the question itself admits multiple valid answers, each capturing different aspects of a relationship too complex for any single framework to fully describe. Either way, the question deserves serious attention. Why reality feels real, why we experience definite outcomes rather than quantum superpositions, why there is something it is like to be a pattern of physical correlations. These questions strike at the heart of what it means to be conscious beings trying to understand the universe we inhabit. They may not have simple answers. They may not have any answers at all, in the sense we typically expect from physics, but they remain worth asking. The discomfort this creates isn't merely philosophical, it touches practical concerns about what we can actually know. When physicists design quantum computers, they must account for decoherence, the process that destroys quantum coherence and forces systems into classical-like states. Engineers build elaborate isolation chambers, cool systems to millikelvin temperatures, shield them from electromagnetic radiation. These aren't arbitrary precautions. They're responses to a fundamental physical process that transforms quantum possibility into classical definiteness. Yet even with perfect isolation, something about measurement remains irreducibly mysterious. The mathematics describes what happens with extraordinary precision. It predicts probabilities, calculates decoherence rates, models how quantum states evolve. But it doesn't explain why those mathematical predictions correspond to the lived experience of observing one outcome rather than another. The correlation between physical process and phenomenal experience remains unexplained. Some researchers argue this correlation needs no explanation. Physical states simply are experiences when viewed from the inside. A brain in a particular quantum state doesn't produce consciousness. It is consciousness, viewed from the first-person perspective rather than the third-person mathematical description. This identity claim avoids dualism while acknowledging that physical description and experiential description access the same reality from different angles. Others find this unsatisfying. Even granting that certain physical states are identical to experiential states, the question of why those particular states have that status remains. Why does this pattern of neural activity correspond to the experience of redness rather than some other quale or no experience at all? The mapping between physical states and phenomenal states appears arbitrary from the perspective of physics alone. Nothing in the mathematical description demands that any physical state should feel like anything. This arbitrariness suggests the connection involves principles beyond current physical theory. Perhaps consciousness is a fundamental aspect of reality, not reducible to particle interactions. Perhaps new laws govern how experiential properties relate to physical properties. Perhaps the framework of mathematical description inherently cannot capture certain aspects of reality, not due to incompleteness, but due to the nature of what mathematics can express. These possibilities remain speculative. No empirical evidence clearly favours one over another. No mathematical framework successfully bridges the explanatory gap in a way that satisfies both physical rigour and phenomenological adequacy. The question sits at a boundary where different modes of understanding, physics, philosophy, phenomenology, all reach their limits without quite connecting. What's striking is that this situation has persisted despite quantum mechanics being the most successful theory in the history of physics. The predictions work, the applications function. Quantum technologies are transforming computation, communication, and measurement. Yet the conceptual foundations remain contested. Different physicists hold incompatible views about what quantum mechanics says about reality, while agreeing completely on what it predicts about experiments. This divergence between predictive success and conceptual understanding is unusual. Most physical theories achieve both simultaneously. When we understand how things work, we typically understand what they are. Thermodynamics explains temperature by revealing it as molecular motion. Electromagnetism explains light by identifying it as electromagnetic waves. The explanation provides both predictive power and ontological clarity. Quantum mechanics breaks this pattern. The predictive power is unmatched, but ontological clarity remains elusive. We know how quantum systems behave. The mathematics is precise and well tested. We don't know what quantum systems are in any way that satisfies traditional physical intuition. The wave function describes something, but what? Probability amplitudes predict outcomes. but what physical process selects particular outcomes from the range of possibilities? Different interpretations answer these questions differently, and no empirical test distinguishes between them. This might indicate that the questions themselves are malformed, that asking what quantum systems really are imposes classical concepts on a fundamentally non-classical domain, or it might indicate genuine underdetermination, where multiple ontologies can account for the same mathematical structure. Either way, the measurement problem persists as a marker of conceptual incompleteness. Not incompleteness in the sense that predictions fail, they don't. Incompleteness in the sense that the relationship between mathematical formalism and physical reality remains unclear. The mathematics works perfectly while resisting straightforward interpretation. This resistance isn't a temporary difficulty awaiting resolution through better mathematics or more precise experiments. It's built into the structure of how quantum mechanics relates to experience. The theory describes correlations between observables without specifying what exists between measurements. It predicts what we'll see without explaining why we see anything at all. The explanatory gap persists because it reflects something fundamental about the relationship between physical law and subjective experience. Consider what would actually constitute a complete solution. It would need to explain not just why we observe definite outcomes, decoherence addresses that, but why those outcomes feel like anything to begin with, why there are perspectives, why experience has qualitative character, why it feels like something to be a pattern of quantum correlations embedded in an environment. These questions don't admit purely physical answers because they concern the relationship between physical description and phenomenology itself. Some argue this relationship is itself physical, that consciousness emerges from information processing, that experience reduces to neural dynamics, that the gap will close as neuroscience advances. This materialist position may be correct, but it doesn't eliminate the conceptual puzzle. Even perfect mapping of brain states to experiential states only describes correlations. The nature of the correlation, why this physical pattern corresponds to this experience, remains unexplained. Others suggest consciousness is fundamental and physical reality emerges from it. This idealist position faces opposite difficulties, explaining why experience takes specific forms, why it obeys mathematical laws, why different observers agree despite separate experiential streams. Neither pure materialism nor pure idealism fully accounts for the relationship between quantum mechanics and experience. The impasse suggests current frameworks may be insufficient. Perhaps the relationships between physical law and subjective experience represents something more basic than either side, something our concepts can't yet capture. Perhaps the question is malformed, asking for bridges between incommensurable domains. Either possibility indicates limits to what current understanding can achieve. These limits appear clearly in quantum technology. Engineers fight decoherence through isolation and error correction, but these are temporary measures against a fundamental process. The same environmental interaction that destroys quantum coherence produces definite measurement outcomes. Understanding one illuminates the other. Yet even perfect control of decoherence wouldn't resolve the philosophical dimension. Why this physical process produces subjective experiences of definiteness rather than awareness of superposition. Some physicists conclude the measurement problem isn't really physics at all. Physics describes correlations and predicts outcomes. Questions about subjective experience belong elsewhere. Philosophy, cognitive science, perhaps domains we haven't yet developed. This boundary respects what physics can address while acknowledging its limits, but boundaries don't eliminate puzzles. Even if physics properly restricts its scope, someone must explain the relationship between physical correlations and experience. If physics can't, what can? Philosophy offers conceptual analysis without empirical purchase. Neuroscience maps brain activity without bridging the explanatory gap. The question doesn't fit existing disciplines. This interdisciplinary character may be essential. Understanding requires both physical rigor and philosophical analysis. Physics provides constraints, mathematical structures, experimental results, theoretical frameworks. Philosophy examines how interpretations satisfy those constraints and what conceptual costs they incur. Neither alone suffices, yet joint effort hasn't produced consensus. After nearly a century of analysis by exceptional minds, multiple interpretations remain viable. Each has defenders who find it satisfying. Each faces objections from those preferring alternatives. No empirical test distinguishes between them. This persistence isn't analytical failure. It may reflect genuine underdetermination, the possibility that questions about quantum reality admit multiple equally valid answers. If so, this represents something unusual in physics. Most physical questions eventually yield to decisive evidence or mathematical insight. Disagreements about details persist, but consensus emerges on fundamentals. The measurement problem resists this pattern. The fundamentals remain contested. What actually happens during measurement has no agreed answer. Perhaps what actually happens isn't the right question. Perhaps the measurement problem asks for something physics cannot provide. A story satisfying both mathematical rigor and phenomenological intuition. These requirements may be impossible to satisfy simultaneously. Mathematics demands precise, testable structures. Phenomenology demands accounts respecting the immediate character of experience. The gap between them might be unbridgeable. This doesn't make physics incomplete in any problematic sense. Gödel's incompleteness theorems prove that sufficiently complex formal systems contain true statements unprovable within the system. The statements are genuinely true, but the system's rules can't establish their truth. Perhaps something similar holds here. Perhaps facts about the relationship between quantum mechanics and experience are true, but can't be established through physical reasoning alone. Physics might be unable to fully explain the measurement problem while remaining complete for its actual domain, describing mathematical structures of physical correlations and predicting experimental outcomes. What additional framework could address the aspects? Physics leaves untouched remains unclear. Various proposals exist: integrated information theory, neutral monism, panpsychism, but none has achieved empirical and theoretical success establishing it as correct. Each makes progress on certain aspects while facing difficulties with others. These aren't merely technical obstacles better theory will overcome. They reflect deep conceptual challenges about relating physical description to phenomenal experience. The challenges persist across theoretical frameworks, suggesting they stem from something fundamental about the problem rather than inadequacies in specific approaches. What remains certain is that reality feels real despite these unresolved questions. The definiteness of experience, stability of perceived objects, continuity of conscious awareness persist whether we understand them or not. The measurement problem doesn't threaten experience's reliability. It questions our ability to explain that reliability in purely physical terms. This epistemic humility may be appropriate. 95 years of work by brilliant physicists and philosophers hasn't resolved the measurement problem. Multiple interpretations remain viable. Fundamental questions about measurement, observers, and the relationship between quantum mechanics and experience remain open. This persistence suggests the problem may lie at boundaries of what current frameworks can address. Future developments might provide clarity. New techniques might distinguish currently equivalent interpretations. Novel frameworks might reveal structures illuminating the relationship between quantum mechanics and experience. Advances in neuroscience might explain how physical processes give rise to subjective states in ways satisfying both rigor and phenomenological adequacy. Or perhaps the measurement problem will persist indefinitely, marking a permanent boundary in human understanding. Perhaps the relationship between physical law and subjective experience represents something genuinely beyond the reach of physics or philosophy alone. Perhaps multiple interpretations will remain viable because the question admits multiple valid answers, each capturing different aspects of a relationship too complex for any single framework to describe. The question deserves serious attention regardless. Why reality feels real, why we experience definite outcomes rather than quantum superpositions, why there is something it is like to be a pattern of physical correlations. These strike at the heart of what it means to be conscious beings trying to understand the universe we inhabit. They may not have simple answers. They may not have answers at all in the sense typically expected from physics, but they remain worth asking precisely because they mark the boundaries where our most successful theories encounter their limits and where understanding must acknowledge what it cannot yet, and perhaps can never, fully explain.